Okay, so let me start with a brief review of dark matter. So the first person to really point out the existence of dark matter was Zwicky. Zwicky was born in Bulgaria. He did his studies in Switzerland and then spent most of his academic career in the United States. And if you go to his birthplace, you'll see this plaque. And it reads, "In this home was born Fritz Zwicky, the astronomer who discovered neutron stars and dark matter in the universe." These aren't the worst accomplishments. And my talk today is going to be on dark matter, but actually neutron stars as well will feature towards the end of the talk. So what does Zwicky do to first find the existence of dark matter, or to find the data suggesting dark matter? He stared deep at the Coma cluster of galaxies. Here's a modern image of Coma. So clusters are collections of galaxies, the largest bound objects in our universe, and you can see galaxies here in this modern image. And he went through the following exercise. Let's just do this as a thought exercise. Let's imagine first that the galaxies are moving really slowly, or that they're not moving at all. So what would happen to the system? The system would collapse because these galaxies are attracted to each other by gravity. So since this system is still here today and stable, we know that this is not the case, and there must be some proper motion with respect to each other. On the other hand, if the galaxies are moving really fast, then the galaxies would just fly apart, and the system would also not be in equilibrium. So because the system still exists, if we know the average kinetic motion of the galaxies, you can work out the potential energy and work out the amount of matter within this cluster. That's exactly what Zwicky went through. And he came to the extremely surprising conclusion at the time that most of the matter in the system is in fact dark. And now, today, we know that around 90% of the matter in the system is dark matter. So this was the first evidence for dark matter, but it wasn't really taken seriously for a while, up until, I think, really the 1970s, when Vera Rubin and collaborators came up with some nice data showing pretty conclusively the existence of dark matter beyond the standard model. So Rubin, who unfortunately passed away just a few years ago, went through the following measurements. So she looked at the rotation curve of Andromeda. Here's a modern picture of Andromeda. So she went farther and farther away from the galactic center of Andromeda and measured the rotation speed of gas. And here is a kind of a modern plot of this rotation curve. Circular velocity is a function of distance. This is for the Milky Way, but Andromeda looks the same. And so what would you expect for the system if there's no dark matter? If it's like the solar system and there's a central object that should fall off like 1/√r. Okay, there's some matter here which extends out, there's a disk. So in fact, you expect it to fall off, but not as fast as 1/√r. But what is observed in data is a flat circular velocity as a function of distance. This cannot be explained by the ordinary matter within the system. And so Rubin and collaborators started to build this picture of spiral galaxies that we have today, of disk galaxies we have today, where these galaxies are relatively small and compact, but they're enclosed within these massive dark matter, massive, mostly spherical, and very big dark matter halos that extend well beyond the size of the actual galaxy itself. So today, dark matter is a precision subject. Some of the strongest evidence for the existence of dark matter comes from cosmology, by looking at fluctuations of the CMB on the largest scales that we probe, scales of hundreds of megaparsecs and bigger. And from this picture, we know that there's around 5 times as much dark matter as ordinary matter in our universe. So these are the largest scales that we probe. A fun question to ask is, what is the smallest size, astrophysical scale, over which you can see the existence of dark matter? So through gravity. So we can't see dark matter in our solar system, because our solar system is dominated by the sun, mostly, and planets. But can we see it if we look at the neighboring star, the neighboring 5 stars? How many stars do we need to see the existence of dark matter? So my extremely small contribution to the subject of finding evidence for the existence of dark matter is to find dark matter on what I believe is the smallest astrophysical scale. This is very hard to find, this result. I don't need it in the data, but it's hard to find in the paper, because my collaborators and I last year, or this year, we were looking for a dark disk. This is a hypothetical structure in the dark matter of the Milky Way. that I don't want to get into. We were looking for this with Gaia. But in the last appendix of our paper, we also measured the local dark matter density. Maybe should have advertised that more than we did. So what did we do? We looked at stars within the local neighborhood, around 200 parsecs relative to the sun. So remember, the closest star is about a parsec away. So you have to go out around 200 times the distance between us and the closest star. And we looked at, we did something very similar to what Zwicky did. Zwicky looked at this average kinetic motion and was able to infer the potential. We looked at the average motion of stars in the vertical direction about the disk, the galactic disk, so perpendicular to the disk. Here's the data that we use. This is the number density profile as a function of the height above the plane and the velocity distribution. And we were able to infer the local dark matter density. Here's our results in the plane of other results on the local dark matter density. So this is the dark matter density, the GeV per centimeter cubed. On the y-axis is a function of the year the observation was made. You combine all these things, you get to this green band, and I've overlaid our measurement in purple on top of that band, which agrees with previous measurements. So dark matter, you might get the feeling that it's this very precision thing, that we need fancy instruments to detect, and fancy people to analyze the fancy data. And on the one hand, that's true, but it's also true that dark matter plays an extremely important role in the evolution of our universe. And I would go as far as to say that dark matter is actually a key ingredient to life, even though we normally don't think of it as one, because without dark matter, we wouldn't have any structure. And here's a simulation, not by me, that illustrates this point. So this is looking at the dark matter density distribution in the early universe, evolving from early times up until today. And I'll play this animation again. Brighter colors here mean a higher dark matter density. And what you'll see is that we start out with small perturbations in the dark matter energy density. These perturbations collapse under gravity. And as they collapse under gravity, they pull in baryons, they pull in ordinary matter, and that ordinary matter makes all of the nice structure like galaxies and stars and us that we have today. So without this dark matter, none of this would be here. So you can see these structures collapsing and forming compact structures. As they're doing that, they're pulling in ordinary matter, which is going to form galaxies. So without dark matter, there's no life, there's no Vera and Zwicky. Of course, these people exist, and we're here, so dark matter exists, that's not the question, but we don't know what it is. And so just to kind of drive that point home, we have no evidence for non-gravitational interactions of dark matter, both dark matter with ordinary matter and dark matter with itself, and also no evidence for any particular dark matter mass. This is what my work tries to address, and this is what this talk is going to be addressing. It's going to be addressing this question of what is the particle nature of dark matter, so how does dark matter fit in with the rest of the ordinary particles, the rest of the known particles of nature. So from a data-driven perspective, when we talk about particle dark matter, there's around 50 orders of magnitude of possible dark matter mass. At the very low end, you have axion-like particles, fuzzy dark matter, mass is around 10 to the minus 22 eV. Here, the quantum wavelength of dark matter is galactic scale. And if you go below here, you start to run into issues because the quantum wavelength is larger than galactic scale, and that messes up observations. At the very other end of the spectrum, you run into the Planck scale. There's nothing wrong with going above the Planck scale, but just the terminology we use is different. We don't say it's particle dark matter anymore. If you allow yourself to look at any dark matter candidate, you can go up another 100 or so orders of magnitude, and you're somewhere over here when talking about black hole dark matter. And we have absolutely no idea where dark matter is in this parameter space. It could be anywhere, and data has told us nothing, which is a little bit discouraging, perhaps. But we do have some ideas. So WEMP dark matter, thermal dark matter, has been perhaps the leading idea over the past few decades. And for good reason. So WEMPs have masses of around the electroweak scale, maybe orders of magnitude around the proton mass. And they're very nice for a few reasons. So WEMPs, from a theoretical point of view, are often tied in with extensions of the standard model, which explain the hierarchy problem, why the Higgs mass is so light, such as supersymmetry. These models often predict a particle, which can be a WEMP dark matter candidate. On the experimental front, we have many different ways of looking for WEMPs, which is also nice. You can try to produce them in colliders, like the LHC, shown here. See them in underground experiments, see them in indirect detection. The problem with WIMPs is that we're very good at doing all these things, we haven't seen anything. So we haven't seen supersymmetry, we haven't seen WIMPs at colliders, we haven't seen anything in direct detection, indirect detection. So I wouldn't say the WIMPs are dead, but there's certainly, there's tension, and they're being cornered. So my perspective on this situation, and everyone has a different perspective, is that we should do two things. There's two things that are very important to be doing right now in the community. On the one hand, we should make sure that we don't give up on our search for thermal dark matter, because it's possible that the WIMP is just right around the corner, and if we give up now, that'd be a bit of a shame if, 200 years from now, civilization's like, oh, they just ran that experiment a little bit longer, they would have found it. And we have a lot of technology. We should make sure we get the most out of this technology, because these are really well-motivated dark matter candidates. On the other hand, I think there's a relevant time to be exploring the rest of this 150 or so orders of magnitude in parameter space. And the community has been doing just that. In my own work, I follow both of these paths, but today I'm going to be focusing on the second philosophy of it, going beyond WIMP dark matter. And specifically, I'm going to be talking about axions. Axions are light particles, ultralight, masses of less than an eV. And they're a very promising dark matter candidate. And I'll try to convince you why. I'll try to tell you why today and convince you these are things worth looking for. So that brings me to the next part of my talk, which is axion particle physics and cosmology. So axions were originally motivated to solve the strong CP problem, charge parity problem. And the strong CP problem is, on the one hand, a very technical problem, and hard to explain if you haven't seen it before. And if you've seen it before, you don't need me to explain it to you. So I was trying to decide on what I could say that would be useful to anybody on the strong CP problem. And I decided to assume that there would be people in the audience who've never seen the strong CP problem and who couldn't understand the QFT explanation of the strong CP problem. And I'm talking to you for the next 2 slides. So to you, I'm going to try to give some hand-wavy explanation of the strong CP problem. And this is a little bit of a stretch because I had to do some analogies here. So bear with me if you find some loopholes or flaws in my argument. So the strong CP problem relates to the neutron electric dipole moment. So before we calculate the neutron electric dipole moment, let's calculate the water electric dipole moment. So water has a charge asymmetry of around 1 over a distance of around 0.1 nanometers. The electric dipole moment, you take the charge asymmetry, you multiply it by the distance, that gives us around 10 to the minus 8 centimeters, just multiplying these numbers together. If you look at data gives you tells us where it's around 0.5 times 10 to the minus 8 centimeters. So that's pretty good. Let's go try to do that to the neutron. So the neutron also has a charge asymmetry of around 1 over a distance of around a femtometer. So let's estimate, multiplying these things together, around 10 to the minus 13 centimeters. If you go through the calculation, it's pretty close. It's 10 to the minus 15 centimeters because there are some pi's in the denominator, and maybe you square those pi's, and that explains the difference between those 2 orders of magnitude. But if you look at the data tells us that there is no neutron electric dipole moment up to this level. And this is the difference between experiment and theory of 10 orders of magnitude. And this complete failure of theory to explain the data is what's called the strong CP problem. And it's a problem because we can't explain the data. So let me get a little bit more technical here. So the strong CP problem, this neutron electric dipole moment, is related to this parameter theta bar, which enters into the Lagrangian for the strong force for QCD, enters in the following way, where G is the QC field strength, G tilde is its Hodge dual, and this parameter you can think of as an angle, which should naturally take values between minus pi and pi. The neutron electric dipole moment is proportional to this theta bar parameter, which naturally should be about pi. And measurement tells us that this theta bar parameter needs to be less than 1 part in 10 to the 10. So I want to say, rephrase this problem in a bit of a subtle way that'll help us explain why the axion can solve this problem. But this might look silly at the moment. Another way to phrase this problem is just to plot the magnitude of the neutron electric dipole moment as a function of this theta bar parameter. And it's trivial, it's linearly proportional. But what you see is that for any value of theta bar, the neutron electric dipole moment would be non-zero, and we happen to live exactly where it's zero. We're fine-tuned to live exactly where it's zero. And so this question is, why are we fine-tuned to live exactly there? So Petchy, Quinn, Weinberg, Wilczek, and others proposed the axion as a solution to the strong CP problem, and I wonder if they made a plot like this before they made their proposal, because what you can imagine, suppose we could turn this into a potential and turn theta bar into some dynamical field, then that field would want to go to the minimum of its potential. And if we could do that, then we could explain naturally why we happen to live at the bottom of this V, if we can turn these things into potentials and turn theta bar into a dynamical field. And so that's exactly what the axion is meant to do. So the axion is a proposed solution to the strong CP problem. This is beyond the standard model. We have no evidence for this, but this is the proposal. So the proposal is to take this theta bar parameter and make it a dynamical field. That field will be called A. Theta bar is dimensionless. A has dimensions of mass. So we need to divide by some mass scale. That's the scale FA. This is called the Q scale, Petchy-Quinn scale. I will refer to it sometimes as the scale at which the axion is created. So if you do this, you'll see that below the QCD phase transition, the strong force QCD generates a potential for the axion. That potential looks like this. And now the axion wants to minimize its potential. It's a dynamical field. And when it goes to the minimum, the neutron electric dipole moment is zero. And anywhere else it would be non-zero, but the special point here is now it's the minimum of the potential. So from a cosmological perspective, what happens in this theory? So at very high temperatures, temperatures around the scale at which the axion is created, perhaps the gut scale, 10 to the 16 GeV, the axion is created. Let's imagine it's originally massless. Stays that way until QCD confines, and then this potential is generated, and the axion gets a mass. And it keeps that mass until today. Some other nice facts about the axion. If we expand this potential, you can look at the quadratic term, and you see the axion gets a mass. And the mass is inversely proportional to this decay constant. And I'll use as a reference point throughout this talk, 10 to 16 GeV, this is the gut scale, giving you a tiny mass around 10 to minus 9 eV. This kind of looks like the seesaw mechanism for how you can take an intermediate scale and a heavy scale and generate a really light scale. Another feature of the axion is that it couples through electromagnetism. This happens model independently through mixing with the neutral pion below the QC confinement scale. There can also be UV contributions to this operator. And it gives a term, AE dot B. You can write this as AFF tilde as well. And this is going to be a really important term in this talk. There's a coupling GA gamma gamma, inversely proportional to the decay constant, although there is some model dependence which can enter into the numerator. So that's axion particle physics. What about the cosmology? And now we have this new scalar field, and we need to include it in our early universe calculations. So before I go on, I just want to point out one difference between the axion as a dark matter candidate and other dark matter candidates you might think about, like WIMPs. So if you're used to thinking about WIMPs, you're used to thinking about particles. And if you've heard axions, you've heard people use the language of fields. And the difference between these two things is this language is trivial, but I just want to be explicit about it. And it's the same reason that we use the language of particles when talking about gamma rays, and we use the language of waves when talking about radio waves. So if you look at WIMPs, each particle is well separated. So the quantum, there's only one particle for each quantum state. The occupation numbers are always 0 or 1. But as you make the mass smaller, then the quantum wavelength becomes larger. At the same time, the number density becomes higher. And so at some point, you transition to the regime at which you have more than one or a high number of particles for each quantum state, a high number of quanta for each quantum state, and then you should transition to using the language of classical fields. This transition happens around an EV, just numerically. And now we're at 10 to minus 9 EV. So we should certainly be using the language of classical fields. Okay, so we have that classical field. I'll call that A. And I want to ask, how does it evolve in the expanding universe? So these are the homogeneous equations of motion for the axion in the expanding universe. So here, H is Hubble, T squared over m Planck in the early universe. There are two simplifications to this equation, which I've made. One, I have put in the gradient term. That'll be important in a second. I'll mention that term in a second. And I also have expanded a sign to leading order and written A. And that'll also be important for something which I'll mention in a second. But if we focus on this simple equation for a moment, I can solve this in real time with one simple limit. That's the limit where at high temperature, so H dominates. I can forget about this mass squared term. Everything else has a time derivative, and the solution is simply A equals a constant. So if I look at the solution of A as a function of time, or inverse temperature, at very early times, the field is a constant. It's frozen at its so-called initial misalignment angle, theta I. This is the initial field value normalized to units of FA. And this should also, you can think of, should also be an angle. You can think of it taking values between, say, minus pi and pi. This remains true until Hubble falls to be equal to the mass, the axion, at which point the field begins to oscillate. And at late times, it's behaving like a damped harmonic oscillator. So it's oscillating at the frequency of the axion mass and slowly redshifting like 2 to 3 halves. The energy density scales like a squared, that's redshifting like t cubed, which is exactly how cold dark matter redshifts. So after the field begins to oscillate, it's behaving exactly like cold dark matter from an astrophysical perspective, making it a good dark matter candidate. You still have to calculate the abundance of dark matter within this scenario. If it behaves like dark matter, but it gives you too little or too much dark matter, it's still not a good dark matter candidate. Here's the calculation of the abundance of dark matter. So in units where this should be about 0.1, you get the correct dark matter density if your decay constant's around 10 to 12 GeV, and your initial misalignment angle is around 1. So I said my favorite value is around 10 to 16 GeV. That means you need to tune this parameter to be a little bit small. There are reasons that tuning could be natural, but I don't want to get into them unless people are interested in it. But the main takeaway from this calculation is that, yeah, you pretty much get the correct dark matter density, making axions a plausible dark matter candidate for actually explaining the observed amount of dark matter in our universe. So the story that I told you has a little bit of a lie in it. In one limit, it's true, and in another limit, it's actually a bit of a lie. So the limit it's true is when the axion was created before inflation. So PQ symmetry was broken before inflation. Because inflation produces homogeneous initial conditions. That's what inflation was meant to do. And if you have homogeneous initial conditions, then it makes sense to forget about this gradient term. I can expand out that sign, and the calculation is exactly what I just showed you. But if the PQ symmetry is broken after inflation, then things are a little bit more subtle. And they're more subtle because after the PQ symmetry is broken, the initial misalignment angle is going to vary from Hubble patch to Hubble patch at the time that symmetry is broken. And then today, if you look at our co-moving horizon today, it includes many different Hubble patches when PQ is broken, which means you have to average over many different misalignment angles. But you don't just do an average, because in between these you get domain walls, you generate topological defects like strings, and you have to account for the full nonlinear potential, and the calculation is much more complicated. It's so complicated it hasn't really been done fully or correctly even today, although this is something that's been known for 30 or so years. So my group has been trying to address this problem recently, and I want to just flash some results, or some preliminary results of this. So you have to simulate this. This is a nonlinear problem, and it's a well-posed problem, but it's very nonlinear, and you have to simulate it. So we've been simulating the axion through the QC phase transition, and trying to look in particular at the spectrum of mini halos that you get at the end of the day. We'll form these compact structures, which I'll show you in a second. This is work with my postdoc, Malte Bushman. Josh Fosher is my grad student. You'll see his work kind of appearing throughout this talk. And late 2018 might now be a bit optimistic, but hopefully early 2019. I guess it already is late 2018. So what are we doing? We're putting the equations in motion on a grid and simulating this story. We're simulating on a grid with around 10 to 10 sites. It's a lot of sites, so we use the Cori supercomputer at NERSC to do these simulations. So we put this thing on a computer, we simulate it, and we see a lot of complicated dynamics that I want to walk you through now. So here's a animation from our simulation. I showed you the animation earlier, which was not ours. That animation was over really big astrophysical scales, like hundreds of megaparsec scales. This simulation is over really tiny scales. The scales here are smaller than the interstellar spacings. So
and what's the mass of the Axion for your simulation?
The simulation is actually independent of the mass.
Okay.
I'm showing you things and coordinates for which we've factored out the mass of the Axion. I can explain that a little bit more in 1 second. I mean, essentially, the mass would come into at what point you stop the simulation. But we can set up the simulation in units where we've taken out the mass and just put it into our final time at which we have to stop the simulation.
But the physics would be unchanged. Like, for example, if you put, probably you used a given range. So, for example, if I take the Axion mass to all the way down to 10 to the minus 22 versus 10 to the power, then...
Good, so this is the QCD axion.
Ah, this is the Q...
This is the QCD axion. So the QCD axion, there is one mass at which this picture works. We don't know what that mass is, so you have to try over a little bit of a range. But you should think that there's maybe some order 1 or 50% uncertainty in what that mass is. Yeah, this is all very specific to the QCD axion. Sorry, I should have mentioned that. So these are very small scales, smaller than between interstellar spacings. Another difference between that simulation and this one, that simulation was a gravitational simulation. The dynamics here has nothing to do with gravity. Gravity is irrelevant for the simulation. All that you're seeing here is the self-interactions of the axion with itself. So let's play this simulation again. What you're going to see, you'll see at the beginning, before, this is through the QCD phase transition, starting right before. Before we'll have strings. Those strings will develop tension. They'll start to connect and form domain walls. Those domain walls will get tension. Then those domain walls will collapse, and they're going to leave behind these oscillatory structures, kind of similar to solitons, which will lead to these compact overdensities. So you can see the strings here in yellow. They're going to collapse, form the domain walls in red. The domain walls shrink down, and then there's some complicated stuff that happens, and at the end of the day, what emerges is the spectrum of compact structures. And these will go on to form compact mini-halos. But I want to move on, and I want to move on because...
Can I just clarify one thing? So it's like the equations are all the same, whether it's QCD axion or not. It's just, but by QCD axion here, you're kind of just focused on this sort of broadish mass range, right? I mean, there's no, like, if you go to like the ultralight scales, the equations are, I mean, they're still the same. They cover the dynamics of it, right? It's just like when you say QCD axion, it's just there's minus 5 eV or something like in this sort of mass range. Is that a correct statement or no?
For the point of view of this simulation? Yeah, so this simulation is actually very specific to QCD because the QCD potential turns on as a function of temperature in a specific way. And we put that temperature in there. So if you want me to simulate another axion, you need to tell me how does that axion get its mass. And if you tell me how it gets its mass and when it gets its mass, then I can do the simulation, but it's going to be a slightly different simulation.
So also, if you have a very small, wouldn't that de Broglie wavelength, if it's too large, wouldn't that be a concern for this kind of simulation?
So again, this is specific to the QCD axion, so we know where the mass is. If you talk about a general axion-like particle, we have to reframe this discussion depending on where the mass is and how that mass comes into being. Is it some UV contribution, or is it from some dynamics in some hidden sector? Given all that knowledge, we can then go through the discussion of does that make sense, and to even set up the simulation, and then how would you set up the simulation. But it's a bit of an abstract conversation without something concrete. Okay, so but for the rest of the talk, I'm going to do what everyone does, which is just to ignore this. Because we don't have the paper out, as I said, late 2018. So we don't actually know what we see. Things could be drastically bad, or things could be really good. So how would things be bad? Things would be bad if all of the dark matter was in mini-halos and no dark matter was in between, or some approximation of that. Then we would never see anything with direct detection unless we happen to be sitting inside of one of these mini-halos, which seems unlikely. On the other hand, there could be new phenomena associated with these mini-halos. These could show up in microlensing, or do something interesting in the context of what I'll talk about with neutron stars at the end of this story. But we don't really know what we're going to see yet. So for the moment, I'm going to assume we're in the first cosmological scenario. Assume that this symmetry was broken before inflation, so we don't have to deal with any of this complicated mess.
What is the scale of these mini-halos?
Masses on the order of 10 to the minus 13 solar masses to 10 to the minus 11 solar masses. That's roughly what we find. In terms of the physical scale, smaller than interstellar space things, but I don't want to say anything too precise because we haven't actually finished. It's a bit of a subtle question to figure that out. So I'm going to talk about efforts to detect axion dark matter, but as everyone else does in this field, and everyone has for the past 30 years, I'm going to assume I'm not in that cosmological scenario, even though we could be. So all of this needs to be reworked in the context of that scenario. Okay, so changing gears a little bit, how do we detect axions? We use this operator A, E dot B. This is essentially what everyone does in this field, and they use it in almost exactly the same way. There are some exceptions to this. Some people look for the axion through its coupling to QCD, but almost everyone looks for the axion through its coupling to QED. And when you read their papers, it sounds like they're doing very different things, but in fact, they're almost all doing the exact same thing. And that is to do the following. Let's put in a static external magnetic field and have an incoming axion, which is going to be dynamical. This can then rotate into an electric field, which is parallel to the external magnetic field. So in pictures, I have a static external magnetic field. My axion comes in, and I convert it to a photon with a specific polarization state, where the electric field is paralyzed perpendicular to the magnetic field. The conversion probability for this thing to happen should scale like G gamma gamma squared, B squared, whatever external value for the magnetic field I have. And then if you just look at the dimensions of this thing, you need some length scale here because the probability is dimensionless. And the difference between different experiments is just what you take for that length scale. So what are the two length scales we have in our problem? They're the geometry of the magnetic field, that's one length scale, and the axion wavelength, the inverse axion mass, that's the other scale. So depending on the experiment, you might take one of these or the other, or some linear combination of both. So let me give you a concrete example of this, which is the CAST experiment. So the sun is surrounded by a KUV plasma. That plasma can create axions at KUV energies. Those axions will free stream to Earth, and they hit the CAST experiment. This is a strong static magnetic field perpendicular to this beamline. And the axions come in, they convert to X-rays now, and we can pick them up with X-ray optics. So what is L in this case? So it's a bit of a subtle question because the axions and the photons have the same energy, but they have different momentum. They have different momentum because the photon is massless, but the axion has a mass. So the momentum mismatch is proportional to ma squared divided by the frequency. So it goes to 0 as the mass goes to 0. So if this momentum mismatch is really small, the mass is really light, let's imagine it's smaller than the inverse size of CAST, then the length scale to take is the length scale of CAST because you can't even tell that there's momentum mismatch. And we're happy because that's a big scale. On the other hand, if the momentum mismatch is really big, is bigger than the inverse length scale of CAST, so it's big mass, then we notice the momentum mismatch. This hinders the conversion, and now the length scale to take is the momentum mismatch scale, which is much smaller than the length scale of CAST, so we're sad because this thing scales like the length squared. So CAST is full of smart people and they know about this, so what do? At high masses, when they enter this regime, they give the photon a mass. They give the photon a mass by putting in some helium-3, some gas, to give the photon a plasma mass. And then they can tune the pressure such that the plasma mass equals the axion mass they're looking for, and they have 0 momentum mismatch, and now the length scale they take is the length scale of CAST. So this is going to be important for something I'm going to return to towards the end of the talk. So here are the constraints on CAST. But before I show you this specific constraint, let me just frame this plot, because this plot is I'm going to reference throughout the rest of this talk. So this is the coupling of the axion to photons, G gamma gamma, units of inverse GeV on the y-axis. This is a function of axion mass units of EV on the x-axis. So 10 to the minus 6 eV is right here, 10 to the minus 9 is somewhere down here. For QCD, the coupling is inversely proportional to the decay constant, Fa, and the mass is also inversely proportional to the decay constant, meaning the coupling is proportional to the mass. And that's what's shown here in this yellow band. And it's a band because there's some uncertainty on what the normalization there is. So QCD lives within this yellow band. That's the QCD axion. People, when they looked at this plot, they thought, oh, I want to make a two-dimensional plot, not just a one-dimensional plot. So let's make axion-like particles, which couple to QED, but don't couple to QCD. That separates out their mass from their coupling to photons, and that opens up the rest of this parameter space. So when you look at the plot, the way that I think about this plot is Axion dark matter could be anywhere in this entire plot. It's not excluded. But the part that's perhaps best motivated is the part in yellow, because that's where I can solve the strong CP problem. So cast, returning to cast, is excluded everything in blue. You'll notice at high masses, the limits get really jagged. And they get really jagged because that's where they've had to put in this gas and adjust the pressure. And there's some air there, and it's a thing you have to do, so the limits get really jagged. The other thing that you probably have noticed is this big green kind of foam sticking down here. These are limits from haloscopes, which I'll talk about next, such as the ADMX experiment, which is a big DOE-funded experiment. And they've done a really good job of constraining Axion dark matter, Axion-like particle dark matter within this range. So what is ADMX? ADMX is a resonant cavity, and they do the same thing. They have A, E dot B with a strong static magnetic field, but now they're looking for dark matter axions, not axions produced inside the sun. Dark matter axions come in, they hit a cavity with strong magnetic field, and they produce photons, but again you have this momentum mismatch problem. But they solve it in a different way. They don't give the photon a mass with the plasma. Instead, they break translation invariance so that momentum conservation works in a more complicated way. Then they're essentially taking the excess momentum from their boundary conditions that they've imposed. So if that sounds confusing, what they actually do is they just match the resonance frequency of this cavity to the axion frequency. And then they can resonantly enhance the photons that they produce and then measure the power coming out. So this signal is very narrow. The axion has a specific mass, and which determines its energy, which determines the frequency. And the corrections to this are around 1 part in 10 to the 6, coming from the fact that the kinetic energy of the dark matter is around 10 to the minus 3 in natural units, and it's not relativistic, so the kinetic energy is 1/2 mv squared. That means you're looking for something with a line width of 1 part in 10 to the 6. So you don't want to build a new cavity every time you change masses. So instead what they do is they put in a tuning rod, and then they can slowly tune the resonant frequency of that cavity. So where are these things going? The next generation experiment following CAST, called IAXO, should, if it operates, do what's shown here in blue, very roughly. ADMX Gen 2, which is this DOE experiment, and a variety of other experiments, should eventually constrain this region shown here in green. And there are a variety of ideas for filling in the gaps going all the way up here to low frequencies, to high frequencies. So the takeaway message from this plot, if the axion exists with a mass above around 10 to the minus 6 eV, the QCD axion, we will find it in the next few years. And that's very exciting. But the other point is that if the axion exists down here, we might have to try a little bit harder. And so I've spent a lot of my time in recent years thinking about how to look for axions in this light mass regime, and that's what I want to come to now.
Kind of important.
Yeah.
Like the warm dark matter bound stops at 1 eV, or the thermal warm dark matter bound stops at 1 eV. Is that correct, or is it 1 kV?
Thermal dark matter is going to be around a keV,
Okay.
a few keV. So yeah, good. So why am I even talking about things at 10 to the minus 9 eV? The production mechanism is not thermal. This is not thermal dark matter. This dark matter is produced cold. It's produced non-relativistically through this misalignment angle mechanism which I described. If this dark matter was produced thermally, it would still be relativistic today. It wouldn't be a dark matter candidate. So you need to have non-thermal production. So my collaborators and I came up with an idea a while back for how to detect this light axion dark matter, and I want to describe this to you now. So we call this abracadabra. Don't ask me to recite what this acronym stands for.
Oh, it's so good. Oh, it's actually something. That's it.
Oh yeah, it's something. The first
wow.
one's I think it's Axion. I think that's probably the
No, it starts with A, as I recall.
maybe it's A, yeah. A broadband, that's right. It's a broadband resonant. Okay, I'll stop there. So we're in this small mass limit. So what do I mean by small mass precisely? The quantum wavelength is much larger than the size of the experiment. Then what we notice, if you write down Maxwell's equations, treating the axion as a classical background field, then the equations simplify in a very nice way. So we come into what's called the magneto-quasi-static limit, which means that I can just talk about magnetic fields and currents, and I can forget about electric fields. So let's forget about this electric field. I would have had del cross B equals 0 in this case with no external current. But instead what I find is del cross B equals something that looks like an effective current. This effective current is proportional to a time derivative of the axion field, whatever magnetic field I already have in the lab, and the coupling G at gamma gamma. And if I require the axion to be the local dark matter density, this effective current is proportional to the square root of the dark matter energy density locally, and it's oscillating at the frequency of the axion mass. And this led us to propose this abracadabra detector concept, which I'll walk you through. The idea is, let's put in a strong external magnetic field in a toroid. The magnetic field is going in a circle. In the presence of axion dark matter, we end up with an effective current following magnetic field lines. This is going to oscillate also at the frequency of the axion mass. So that this effective current generates a real magnetic field. By the right-hand rule, that magnetic field comes outside the center of the toroid, where there was originally no magnetic field. And it's piercing the center of this toroid. As this current oscillates, the magnetic field will oscillate up and down. So if I put in a pickup loop in the center, as that magnetic field oscillates, it induces a changing flux, and that induces the current within that pickup loop, which I can try to detect. So that's the idea. We since formed a collaboration, the abracadabra experimental collaboration, to build a prototype for this experiment. The experiment, the PI, is Lindley Winslow at MIT. That's where the experiment physically is. Consists of a few institutions. At Michigan, our job is to analyze the data. So all of the data is collected at MIT and is shot straight over to our servers at Michigan, where we look for dark matter. So we built a 10-centimeter prototype of the experiment. We actually have results, which I'll show you in a second. So here is the experiment. It really looks like that toroid that I drew. You can see it goes in a circle. Here are the superconducting wires that source that magnetic field. Put it in a superconducting cover, put it into a dilution refrigerator. So this is a 10-centimeter experiment. It can literally fit on the palm of my hand. So it's a palm-sized dark matter detector. We didn't actually expect to find dark matter with this experiment. We just wanted to demonstrate the technology so that we could eventually build a bigger experiment. So here's the data, some preliminary data that just came out. You can read about it in this paper here. So here's our raw data. This is pickup loop flux as a function of frequency. We focused on this frequency range between around 100 kilohertz and a few megahertz. So these are laboratory frequencies, which is the nice thing about this. And when I saw this plot, I got really excited. So blue here is our data. Flux is a function of frequency. Green was our rough expectation for what our noise should be. And that green line is coming from quantum noise within the squid, the device that we use to pick up the current. You can see that our data in this frequency range is roughly at the level of quantum noise, so we're quantum noise limited. With some exceptions, at high frequency we get these bumps here, probably coming from someone's cell phone penetrating our shielding, and at low frequencies there's also some noise coming from vibrations, most likely. But within this frequency range of interest, we're pretty much dominated by quantum noise, meaning that we can scale. We understand our noise, we're limited by quantum noise, this experiment then scales. The other nice thing is that we didn't find any dark matter. So this is our limit on the coupling. G gamma gamma, axions to photons, is a function of mass. In green and yellow, this is our expectation for the limit under the null hypothesis. In black is our data. This is a subset of the data. This has been downsampled by a factor of 10,000 because there's roughly 10 to the 6 independent points per decade. But we don't find any evidence for dark matter, which is pretty impressive. We tested around 20, 30 million independent points. All of them were consistent with the null hypothesis. So there were no extra lines that we couldn't explain. So when you scale this out, it doesn't look quite as impressive. This is the coupling of the axion to photons again, it's a function of mass. But now here is ADMX in solid red. This is projected future ADMX in lighter red. So before I was showing you up here, now I'm down here in this low mass regime. So that's 10 to the minus 9 eV, my favorite mass. So what are we planning on doing? Right now we're doing this. Turns out our limits were around a factor of 10 weaker than expected. And that factor of 10 roughly factorizes into a factor of 2 and a factor of 5. Factor of 2 is because someone built a wire too small. And the factor of 5 is because someone put an inductor too close to another inductor. So these are fixable things. So the experiment is opened up right now, and these things are being fixed. And after they're fixed, our sensitivity should be in green. At the same time, we also plan on going to higher frequencies, I don't know how far yet, and to lower frequencies, I also don't know how far yet. And we also plan to switch over to another sort of readout mechanism that uses a resonator to get increased sensitivity at high masses. This is funded, this is happening right now. The paper from this will probably be out in mid to late 2019. What do we want to do in the future? So now I'm going to speculate, because none of this that I'm going to talk about is funded. We want to build something that's bigger, because our sensitivity scales like volume. And on kind of the 2020-ish time scale, what we would like is a 75 centimeter version of this experiment, which with this resonant readout would get us down to the QCD Axion range. This is where we actually expect to see dark matter. And on kind of a similar time scale, we would like a 1-2 meter-ish size experiment that would get us down the rest of the way. There's a gap here, but we know how to fill in that gap. So with order $10 million-ish of money, we think that we could cover everything from around 10 to the minus 9 eV all the way up to 10 to the minus 6 eV, which would be really
So
nice.
you can go further down along this x-axis, right? You don't need to stop at 10 to the minus.
In practice, there are issues.
Yeah.
There are issues, yeah. There's noise sources. Noise gets way harder as you go to lower frequencies. You could work really hard and maybe extend this a little bit, but
So
even
this line is a solid cutoff. What?
it's not a solid cutoff, but it's probably optimistic even what I'm showing you here. Notice we had to stop here now
Yeah,
because
yeah,
vibrational
yeah.
noise. So we think we can go down a little bit more, but I don't know how much more. If you really wanted to do it, you probably could by using some LIGO style vibrational isolation. But for our purposes, we're really focusing on this region and for the QCD Axion. Okay, so in the last few minutes, I want to tell you about another idea. So if you're used to thinking about limp dark matter, there are all these ways we have of looking for dark matter in addition to direct detection, which is what I've been talking about. For example, there's also indirect detection, and you might ask, is there any equivalent of indirect detection for axions? And I think the answer is yes, and I've been working on something I'm very excited about, and I want to show you a little bit about that today. And the idea is going to be to look for radio lines, so again, we're in the radio frequency, we're always in the radio frequency here, from axion dark matter converting into radio photons and neutron stars. So this is work that came out over the past year in 2 papers. The first was with Anson Hook, who is now at Maryland. Yomi Khan is at Chicago, but is moving to UIUC as an assistant professor next year. And Jishun Soon, who's an undergraduate at University of Michigan. And then there was a more recent paper with the same undergrad, and Alex Chen, who's a postdoc at Princeton, who works on neutron star simulations. So what are we doing? Before I tell you what we're going to do, let me just sell you the final product and then explain what you bought. So here is the coupling to photons as a function of mass. This is ABMX again. We think that with radio observations of known targets, with things like GBT or the future SKA, we could do something like what's shown here in black. So that would be pretty crazy. We can cover a significant chunk of the best motivated region of the QCD Axion parameter space, not with $1 billion scale new experiment, but with existing radio telescopes, just pointing them in the right spots and analyzing the data in the right way. So this looks very nice. So what is actually going on here? So I'm going to be talking about neutron stars. Here is an artistic rendition of a neutron star. And neutron stars have strong magnetic fields. That's why I'm looking at them. They have very strong magnetic fields. The strongest really in our universe, certainly stronger than anything we can create in the lab. Neutron stars are also surrounded by plasma. So you can even see that a little bit in the artistic rendition. I don't know if that's on purpose, but you can think of this purple stuff out here as being the plasma in the magnetosphere consisting of electrons, positrons, and ions. So this plasma gives the photon a mass. And that mass increases as you get closer to the neutron star because there's just more stuff as you get closer to the neutron star. And this turns out to have a very nice implication. So if you imagine ambient dark matter, it's going to fall in towards the neutron star just by gravity. And at some point, you're going to get resonant conversion of axions to photons. That conversion happens when the photon mass equals the axion mass. And that's what we'll call the conversion radius. So just to plot this, the axion mass is a constant, but the photon mass is rising, and at some point they're equal to each other, and then you get resonant conversion for the same reason. The CAS got resonant conversion. So what does this mean? Again, the conversion probability is b squared g squared L squared. And the non-resonant case, which is always there, L is the inverse mass. It's the quantum wavelength of the axion. In the resonant case, it turns out the relevant length scale is the geometric mean of the inverse mass and the radius of the neutron star. The inverse mass might be 10 centimeters. The radius of the neutron stars is 10 kilometers. And you square this thing, so you buy yourselves many, many orders of magnitude in the conversion radius and the conversion probability if you have resonant conversion. And out from this, you get radio waves. And these radio waves are going to be at the frequency of the axion mass. So at the frequency of the mass, they might be redshifted a little bit by the line of sight velocity of the neutron star with respect to us. And then the width of the line is set by the velocity dispersion of the dark matter. And that's because the dark matter is non-relativistic, so the energy spread scales like v squared, and v you should take in the galaxy to be around 10 to the minus 3. So these lines are around 1 part in 10 to the 6 wide. The same reason that they're 1 part in 10 to the 6 wide for ADMX. These radio waves then propagate to Earth, where we can look for them as narrow lines with radio telescopes. So what would you expect to see? Just an example, if you pointed at, for example, the galactic center. So here is an example of the flux density that we would observe in Jansky's as a function of relative frequency, looking at the galactic center with these parameters for the mass and the coupling. And the point is that there are many neutron stars at the galactic center. And they all emit at exactly the same frequency, almost, except for the line of sight redshift coming from the relative velocities of the neutron stars. So the difference between red and black is this is the difference between two different neutron star models. So let's just look at the red one. Each of these lines is a line from an individual neutron star. These lines are 1 part in 10 to the 6th wide. But the overall width of this thing is 1 part in 10 to the 3, because that's how the neutron star velocities are distributed. The neutron stars are traveling at 100 kilometers per second or so. So each one of these lines is an individual neutron star. So if we stare at something like the galactic center, we would expect to see a forest of lines spread out over some relatively narrow width of frequency. So that sounds great. Can you actually do it? So that was our question. And luckily we had a friend of a friend who was taking data on the Effelsberg radio telescope in Germany. And we were able to convince him to save data in the format that we needed so we could look for axions. And he did. It filled up their server, and he got a very angry email, generated about 100 terabytes of data, because we had to read out at 1 part in 10 to the 6th frequency resolution, which they don't normally do. But we took the data away very quickly before anyone got too mad. So this is Ralph, who actually took the data. Josh Foster is, again, that same grad student. He was also the one who actually made that limit plot for abracadabra. Myself and Christoph Vinegar, who is at Amsterdam. This is in progress. So we have 1 hour of observation time towards the following magnetar, which has some very nice properties. It's around 0.1 parsecs away from the center of the galaxy, meaning we expect a high dark matter density. And it has a very high magnetic field due to the magnetar. We took data at 3 kilohertz resolution at a frequency of 2 gigahertz. And we vetoed RFI, radio frequency interference, so spurious lines, by switching on and off between the target, away from the target, away from the target. And if we saw a line appear both on target and off target, we vetoed that line. And here is a very preliminary plot of our limit that we set. We saw no significant detection, no significant signals which we couldn't veto with the off data. This is preliminary. The other plot that I showed you also had preliminary on it for abracadabra. That was preliminary because the paper is collaboration. The paper hasn't been accepted yet, so I have to say it's preliminary. This is preliminary in the sense that this plot is is going to change. This is preliminary in the real sense of the word preliminary. This is kind of our first pass at this plot. There are things here which I know aren't quite right. This will shuffle around a little bit, but morally speaking, this is where it's going to end up falling. So this is our limit on GA gamma gamma. This is again the projected future ADMX here. And within this narrow range, we see no evidence for dark matter, and we can set this exclusion. This was, again, data we kind of got from a friend. We just got a proposal accepted for the Green Bank telescope to do our own observations. With those observations, I think we can do a lot better and cover some big chunk of the QCD line. Okay, so I want to conclude just by putting all of this on the same plot. So here is our radial limit so far. Doesn't look so impressive when you zoom out, but I think, especially going into the future with SKA, but even with GBT, we'll be able to cover some big chunk of the QCD line. And here, just for reference, are our current and projected sensitivities from Abracadabra. Up here, I told you there are ideas for covering this region of parameter space. Down here, below 10 to the minus 90 eV, there's also ideas, such as Casper. This is an experiment some people might have heard of. Looks for the axion coupling to QCD. Also black hole superradiance, some people might have heard of. And then below this purple line here, below around 10 to minus 11 eV, you shouldn't be talking about the QCD axion anymore, because the decay constant's above the Planck scale. So the game stops here. The game extends from this purple line up to here. And the exciting thing is we as a community have ideas for covering this entire range of mass. So if the axion exists, we probably shouldn't have seen it, but we will in the next few years. That's very exciting. I'll stop there.
Are there any questions? Just a quick question. So there are these nuclear magnetic resonance experiments too that are supposed to cover this low mass axion regime. Was that on there?
Yeah. So
that's Casper. Okay.
Casper is one of those. Yeah.
Okay. And the other thing is for your simulation. I think the answer is probably no, but like for your simulations, going back to you can't like resolve like the. You said you can maybe resolve like the size of these. Let's call them mini halos. Can you resolve like this density structure and then like the central densities? I mean, are you able to do that? You think?
Yeah. So we do.
Okay.
The reason that I was kind of hedging a little bit on the answer to that question earlier is that simulation stopped at a temperature of around 50 MeV or so, capital M.
Okay.
You then have to evolve those overdensities until today. And that evolution at late times is gravitational.
Yeah.
So we're predicting the initial conditions that will be used in an in-body simulation. My group is also doing those in-body simulations, but those are now gravitational in-body simulations that you have to do. So I can tell you the math very precisely because there isn't much mass loss in that process, but the density profile at the end of the day is going to be determined, yes, by the initial conditions, but also by gravity at late times.
I mean, is that really true? Because I mean, let's say NFW profile gets set up by just some set of circumstances in which the halo collapsed initially, right? And the thing evolves, the halos might get stripped and blah blah blah, right?
Yeah. No, so there'll certainly be some evolution, but these are a little bit different from NFW profiles in some sense because the individual halos tend to collapse into compact structures like essentially right away. A lot of these things will decouple from the rest of, they'll hit matter radiation equality significantly before the rest of the universe. And so then they start collapsing, you get these compact objects. So I have a feeling, but again, we're just doing these simulations, that the halos that we'll get will be more granular than what you're used to thinking of for lambda CDM. But again, this is on very small scale. So the lambda CDM structure is of course still there, and this structure is on some much smaller scale.
I mean, I guess gravitational lensing could come in then.
Yeah, so lensing, microlensing is something that we were originally thinking about, and I think we understand this well. There had even been some claims in the literature that microlensing constrained this scenario. And I think we understand the results well enough at this point to say that that's not going to be the case. These things aren't dense enough to actually to have already been constrained by microlensing. Maybe some future microlensing survey could say something, but they're certainly not dead from microlensing.
Does this resonant production that you're looking at in the radio telescope, is that already accounted for instance, in solar axion production as well? You get that resonance back to the other direction?
Yeah, so
Because it would be super exciting to constrain the QCD axion along this band without assuming that it's cosmological.
yeah, so the short answer is no. So let me explain that a little bit more. So for CAST, what CAST does is it uses the sun as a source of axions.
Right.
Those axions have energies around a keV. Those axions come to Earth, and they're detected at Earth. And within the lab, the resonance is resonant. So we're doing as good as we can in the lab. There are alternate proposals for looking for the solar axions, which involve using the solar magnetic field to convert the axions directly within the sun, within the outer part of the sun, into X-rays, which you can then see with the new stars. So I know the new star is doing a search, which is an X-ray telescope, is doing a search for this. It's a little bit more subtle because it's not zero background. If you stare at the sun in X-rays, it's incredibly bright. So you're looking for some spectral changes to the frequency spectrum.
But I just mean treating the sun as a source. If there's a resonant conversion at some depth in the sun, you might be getting more axions than you might even guess.
Yeah, but so the production mechanism is a particle production mechanism. So there's no resonance in production. So you can't you're not resonantly producing the axions because these are not dark matter axions. These are axions which are being produced in some Bremsstrahlung process. So the resonance would need to come in detection. And in the laboratory case, we're detecting in the lab, we're already resonantly detecting. In the solar case, you also, resonance also does not play a role. So I don't know if the same thing that I'm talking about really plays a role in the sun. I know of one astrophysical case in which it could have played a role, but it turns out it doesn't for a subtle reason, and that is, if you look at the crust of a neutron star, the crust of a neutron star also produces keV axions. It's keV plasma. If you tune the temperature of a neutron star to be old enough, it'll be a keV plasma. And you can ask whether those keV axions can resonantly convert within the magnetosphere. For a while back in the 80s, people thought that they did. And then in the late 80s, people realized that they do, but there's also a strong field QED effect, which suppresses the conversion as well. So it didn't work. But yeah, the short answer is as far as I'm aware, this is kind of the only place where this resonance regime really matters. And it's kind of specific to having axions in dark matter. But on the other hand, if you're above 10 to the minus 6 eV and above here, the axion is dark matter. There's essentially no way to avoid it, because the problem you're faced is the axion is too much dark matter. So you have to explain why there isn't more dark matter. If you're down here, then naively the axion isn't all dark matter. So maybe the axion could exist and not be all of dark matter. Up here, I would be incredibly surprised if the axion existed and was not all dark matter, because that seems like a pretty tuned scenario.
So what's the impact of, if Age's result is correct, then what's the impact of that result to all these axion scenarios?
And it's dark matter?
Yeah.
Okay, let me answer that more generally. If somebody else detects another type of dark matter, then to some level, yes, that certainly is less motivation to look for another type of dark matter. I don't personally think that Edges is super compelling as a dark matter scenario. It's much more likely a systematic. Yeah, if we see something in the LIC, or if we see something in a direct detection experiment, or an indirect detection for another dark matter candidate, the prior probably shifts on axions. And the same can be said if we see something in an axion experiment, the prior is going to shift on other dark matter candidates. There are scenarios in which you expect dark matter to be amongst multiple things. So from a kind of broad scientific perspective, I don't think if we see axions, we should give up necessarily on the search for WEMPs, and if we see WEMPs, we should necessarily give up on the search for axions. Because especially when you get into kind of more anthropic scenarios like split supersymmetry, Sometimes you actually expect to see both axions and WIMPs. But at that point, it's kind of a philosophical and
No, I was more
conversation.
asking from this photon axion coupling. Would that impact this low temperature?
I don't think you can get anything that would be observable in the CMB from any of this parameter space here.
It's too small.
These are too small. Yeah. Yeah. If you let yourself go up here somewhere, and then you play additional games, maybe bring a